Okay, let's start. It's my pleasure to present today our speaker, Schilling from Ludwig Maximilian University of Munich. Right, so Christian is doing a lot of work in quantum information, particularly related to quantum chemistry or electronic structure or many body problem physics. So he is Emily Notter research group leader actually in LMU, and he did his postdoc with Vladka Vedral at the University of Oxford. Also, he did another postdoc with Dieter Judge and on Oxford as well. So he did his PhD at ETH Zurich, and I guess all this in all these places, his career path was more or less along the lines of quantum many-body and information theory, and so it's a very exciting combination, and hopefully we'll learn today more about that.
Yeah, thank you very much, Arthur, for the introduction and also for the invitation. It's really nice to be here in Toronto. I really enjoyed the time here so far very much, and I would like to use this opportunity today to provide the overview presentation over the research of my group. It has been done the past 4.5 years since our arrival in Munich. As Arthur pointed out correctly, so our research is concerned with the interface of quantum information theory and quantum many-body physics. And today I try to convince you that this interface will be very, very exciting for all of us. Because it's about combining the positive and fresh ideas from both fields to come up with novel ideas. And the main theme of our research, the main topic is actually this ground state problem. Let me actually briefly introduce this to you or recall it. So you consider so many interacting fermions subject to some external confinement potential. So I have here in mind the potential created by the nuclei, for instance, in a molecular system or in a solid body. Okay, and there are many scientific questions you can ask about those systems. You can ask how does the system evolve in time? What are the excited states? How does it respond to external perturbation? And this is all very, very important from a practical point of view. But even before you're going to ask these important questions, you should first understand what are the ground state properties of such a system. So it's about essentially zero temperature physics. Okay, and this is actually not that irrelevant to answer this question about ground state physics, because for instance in quantum chemistry, if I tell you there are a few atoms which you put together to form a molecular system, you may wonder, what is the geometry, the equilibrium geometry of that system at low temperature? So this is about ground state. You need to calculate the ground state energy for different geometries, arrangement of the atoms, and then you find the lowest energy, and this tells you what is the equilibrium geometry. Also, if you recall, both Einstein condensates described a small quantum depletion via the Bogoliubov theory. If you determine then, or if you find the right approach, the ground state physics, it also tells you about the low-lying excitation spectrum. So you see, this indicates that if you just ask about the ground state energy, which could be addressed by minimizing the energy excitation value over all infinite quantum states, you can already learn a lot about the properties of the system. Okay. And in principle, you would need to minimize this energy excitation value of your system over all infinite quantum states of psi n. And here the problem comes into play, namely when you increase the system size, when you add more and more fermions to your system, when you approach the thermodynamic limit of a solid body, the Hilbert space dimension grows quite drastically. You get this exponential scaling. And from that point of view, it seems at first sight that this problem is pretty hopeless. So if you want to diagonalize an emission matrix on an exponentially large space, you cannot do it. But as you also know, in practice, there are some potentially simplifying structures. So I have here two quite obvious structures in mind. So the first one refers to the so-called Hartle picture. It's based on the formalism of first quantization. Okay, so independent of the number of fermions you have, even like 10 to 23 fermions in quantum chemistry, also in quantum matter physics, they interact typically only by pairwise forces. You see only electron I and J coupled to each other, and then you sum over all electron pairs, and these two electrons are coupled by a pair potential Wij. For instance, the colloid interaction or the Hubbard on-site interaction. And now you can change the perspective to the orbital picture or mode picture or site picture, which is based on the formalism of second quantization. And there, it's not about asking how do two electrons couple, it's about asking how do two orbitals or 2 points in space couple to each other. And then you know, if you refer to the Coulomb acting potential, when you separate the 2 points in space further and further, the coupling between them gets weaker and weaker. So this is a different structure, okay? And then it's actually, if you think about it, it's a very natural task, and this is exactly my motivation for our research from the past 5 years, and maybe for the next 10, 20 years, to, in the first place, explore and quantify via quantized quantum information tools the consequence of those two structures, okay? And then finally, we would like to exploit them in order to propose a more effective approach to the ground problem. Okay, so this means we would like to exploit the consequence of these two structures to their full potential and on the same footing. It's actually all methods that have been developed the past 90 years in physics, chemistry, and material sciences, they de facto focus either on the particle picture or on the orbital picture. I can give you some examples. Since on the particle picture, a very famous method is density function theory. That refers to the essentially the one particle reduced density matrix and then even the diagonal entry like the density. On the other hand, this, as you also may know, the density matrix renormalization group ansatz, which refers to second quantization, where it's about exploiting the local entanglement on the lattice side basis. But there's hardly any approach which deals with those two structures in the same footing. It's always like one structure first, like DMRG for some active space, and then use perturbation theory to deal with the particle collation, or vice versa. And it's the ultimate goal for us to really take these two structures equally seriously. And therefore, the outline of my presentation will be the following. So there will be two parts. First, in the first half, we're going to discuss the particle picture, the second half, the orbital picture. And in each of those two parts, there will be 3 sections, okay? In the first section, I would like to recall or give you some ideas how people in quantum many body and quantum chemistry were already exploiting these two structures, okay, to simplify the ground state approach. Then we change perspectives completely to quantum information, and we are asking, can we actually talk about entanglement and collation between particles? Does it make sense? Or does it make sense at least to talk about collation and entanglement between orbitals? Okay. And then last but not least, and this will be the most exciting part, we're going to combine the quantum information and quantum chemistry, quantum mechanics perspective to a kind of more unified perspective, okay? And then I would like to give you some ideas how fruitful this can be by sharing with you some of our research highlights from the last 5 years, okay? This is like open end, so it could maybe hopefully also inspire you that you have some ideas how to use the different positive aspects of these fields to come up with new ideas, okay, in your research. And again, as a last comment, if you have a system, I mean, at the end, you can describe the ground state or the system in general correctly in either first quantization or second quantization. So at the end, there must be a connection between these two pictures, okay? So I briefly comment on the bridge. And you should always keep in mind throughout this talk, the ultimate motivation is to come up with a more effective approach to the ground state problem, okay? Which should all serve this purpose. So let's start with first quantization, okay? So this is like a general perspective on the particle picture, also includes part of my motivation for some of our research. So to obtain the ground state energy, we minimize the energy expectation value over all n-fermion particle states. So from a mathematical point of view, if you like, you could skip the purity, okay, and really allow for all n-fermion quantum states. I mean, it's maybe practically not a good idea, but from a mathematical point of view, it has the advantage that then we get here a very beautiful convex set. Because the convex combination of any two density matrices is again a density matrix, as you know. And then here you're just talking about, you're just considering here a linear function on this space. You minimize it, and then because of the linear function, you automatically end up on the boundary of this convex set, and this is in the ground state, and its energy is the ground state energy. Okay, but now you can exactly make use of this simplifying structure in the particle picture. Because if you look at this, there's like macroscopically many fermions here, but the Hamiltonian contains only 2 particle terms. So for free, you can integrate out all fermions except 2 and address exactly the same problem through the much simpler 2-particle reduced density matrix rho 2. Okay, this guy lives on a much smaller space. Okay, it's a tremendous simplification, but it does not trivialize the ground state problem, because now a part of the complexity of the ground state problem is now hidden in the boundary of this set here. Because indeed, if I give you a two-particle density matrix for two fermions, it's not automatically one which corresponds to an n-fermion quantum state. There are so-called two-body energy constraints, which are reducing the set of all two-particle density matrices to a non-trivial subset. And in principle, it's very complicated actually to describe the set of admissible two-particle reduced density matrices. But now you can go one step further. And this is actually my vision, which motivates a part of our research on functional theory. Because imagine someone actually managed to solve this problem here and really found a compact description of the set. I mean, this is not possible, it's mathematical proven, it's computationally hard. Okay, but let's imagine someone tells you, gives you a compact description of the set. Well, this would actually allow you to solve the grounded problem, not only for Coulomb paired acting systems, but for every paired acting system. You can write down completely absurd type of paired acting Hamiltonians that no one cares about in physics or chemistry, and you can also solve it. So this, in that sense, it's a complete overkill to solve that problem. It's not what we need in physics or chemistry. And indeed, if you talk, for instance, to quantum chemists, you know, they're living like every scientist in their own world or a part of their own community. They care essentially only about Coulomb acting system chemistry. Quantum matter is always typically about Hubbard on-site interaction. So from a mathematical point of view, you could say, well, your whole life is about studying Hamiltonians of this form. I mean, you have a varying particle number, which you now keep fixed, particle number n. But what's crucial is that the paired action W is fixed for your whole life, okay? It's Coulomb action, let's say. And then you could say, well, then you study different experimental potentials for your molecule. And in modern quantum matter experiments, you can also vary maybe the hopping rate, or in the field of ultra-cold gases. This is not so uncommon. So you could say, if you're maximally ambitious, you would like to solve the grounded problem for any choice of a one-particle Hamiltonian H1, and W is fixed. And now I ask you, what is the conjugate variable to the one-particle Hamiltonian? Okay, so this means, what is the most primitive quantity, or what's the most primitive aspect of the wave function that you need to know in order to calculate the expectation value for each one-particle Hamiltonian? Is it the wave function? Well, the wave function contains too much information. The 2RD would allow you to do the job, but it's also too complicated. So it's actually the one-particle reduced density matrix. So you can trace out another fermion of the two, and then you end up with the one-particle picture. And indeed, maybe given this motivation, it should not be surprising to you that there exists a so-called one-particle reduced density matrix functional theory. This is an exact theory in principle for addressing the grounded problem in the following way. So I give you rho 1. Of course, you can calculate the expectation value of every one-particle Hamiltonian, like potential energy, kinetic energy, in an exact way via this formula here. But now the amazing point is that there exists a universal function which depends only on rho 1, and it's parameterized by the fixed W pair induction. Okay, no one knows this function. It's also very hard to approximate it. But the good point about this is, you know, this function exists and it's independent of H1. So this means the entire community of quantum chemists, in principle, they could dedicate a lot of effort, a joint effort, to approximate the same function that everyone cares about. And then 10 years later, they can use this function to solve the grounded problem for the next 50 years in their life for all millions of systems that they care about. So it's a very economical functional theory, because one can exploit the fact that the W is fixed. Okay, this is quite the opposite for wave function methods, where different calculations are more or less independent of the fact what the pair interaction is. But what's maybe even the more important take-home message from this slide is that by talking about ground state physics, I identified the one-particle reduced density matrix as the key object, as a very, very important quantity. So now let's change perspective. Let's forget about physics and talk about quantum information. So I'm wondering, does there exist a notion of entanglement and collation between electrons or fermions? Because, you know, chemists, they talk all the time about electron collation. I'm wondering, is there some foundation for this? Do we know what this should mean? And in order to make this potentially precise, let's recall actually what quantum information scientists know about. Namely, they have a very concise notion of entanglement between distinguishable particles. So let's say, for simplicity, it's a bipartite system, Alice versus Bob. Alice and Bob have local Hilbert spaces, HA, HB. So the joint Hilbert space for Alice and Bob is given by the tensor. So I'm assuming here finite dimensional Hilbert spaces to avoid some mathematical subtleties. So then on the level of the algebra of observables, the same holds true. You just take the tensor product of the algebra of Alice system, the algebra of observables of Box system, and take the tensor product, and then you have the algebra of the bipartite system AB. So now, what do we mean by a quantum state to be uncorrelated? Well, on the one hand, you could say it just means the density matrix rho AB is given as a tensor product of reduced state for Alice and one for Bob. But somehow, if you apply it to more complicated scenarios, let's say to fermions at the end, there's some kind of caveat because not every Hermitian operator is an observable at the end. Therefore, you should look for a slightly more precise definition of uncorrelated states. And the most concise way to talk about this is like the following definition. So Alice is performing a measurement on her side of so she's measuring an observable that exists physically speaking. Bob is measuring observable B on his side. Then we look at the joint expectation value of this measurement, and whenever this expectation value factorizes into a product of two separate expectation values, for any choice of measurement A on Alice's side and B on Bob's side, then the corresponding quantum state rho is called uncorrelated. This makes a lot of sense because then the measurement expectation values are independent of whatever they do in Alice and Bob. So now let's imagine an experimentalist flips a coin, and depending on the outcome, on the two outcomes, the experimentalist prepares either one product state or a second different product state. Okay. Well, in that case, the respective quantum state, if you don't know what the outcome of the coin flip, it's actually a quantum state which contains a correlation, but it's only classical correlation. So there should not be any quantum correlation. This exactly, to some degree, motivates the idea of entanglement. So you could say a quantum state is called unentangled if it can be written as a convex, as a classical mixture, as a convex combination of product states. So now the ninth point of this picture here, or this definition is, it can give rise to a very beautiful geometric picture of quantum states, which is illustrated here. So in light blue, very difficult to see here, you see the set D of all bipartite quantum states. Okay. There's now a subset shown in black, D0. These are all the uncorrelated states. And the convex hull, illustrated in the cartoon, here as a blue triangle, it's like the smallest convex set, which contains the black set. Okay? This is now the set of unentangled states. Okay, so far so good. But this picture now allows you to propose, at least on a formal level, methods for correlation and entanglement. So you give me a state rho, and I just tell you, well, measure formally the minimal distance C of rho to the set D0, and the distance E of rho to the blue set, and just call it correlation or total correlation in the sense of classical plus quantum correlation, and E of rho is the entanglement. Okay, so these are so-called geometric measures for total correlation and for entanglement. Okay, in practice, very difficult to calculate, particularly entanglement. For mixed states, you can never calculate it except for very small systems, but this is just like how it goes in quantum information. It's a very abstract field, and they propose a very precise concept, and then at the end, maybe you cannot calculate them, but you can talk about properties then. And in physics and chemistry, it's more the other way around. You would like to calculate something, then it's maybe slightly ill-defined. Okay, so this is like a mismatch, but this is how it goes. So now let's go back to fermions. We understood now the necessity of having somehow a tensor product structure. I think it's even more complicated, so keep it simple here. But you look now at the n-fermion Hilbert space HM. For fermions, as you know, there's no tensor product, technically speaking, because you have the exterior product, the wedge product. So you have like somehow n copies of H1, and then you anti-symmetrize it. So if you study this space from a first quantization perspective, there is unfortunately no tensor product. And then you have to take this very serious. You have to conclude that because of this, there does not exist a notion of entanglement or correlation between the fermions, because there's no tensor product between the H1s. Okay. So, and you then talk again to the chemists, they're not so happy about hearing this because they would like to talk about electron correlation. So, but we already understood now this idea of electron correlation, whatever it will be at the end, it cannot have the same rigorous character as proper entanglement, because proper entanglement refers to a notion of subsystems, and fermions are not proper subsystems of a large fermionic system. But we want to still satisfy the chemist and want to define something rigorously. And then it's very clear what chemists and physicists have in mind. They refer to a state as being uncorrelated, have zero electron collation if it's the ground state of a non-interacting Hamiltonian, non-interacting electron Hamiltonian. And these are exactly the slated determinants. So you see here, take the vacuum state at grade n fermions, 1, 2, 3 up to n, in n different one-particle states. Could be spin orbits, could be lattice whatsoever, momentum states, spin up and spin down. And then you just have an entire monomial of gradation rates here. Or this is another way to write or express my slated determinants. And then the manifold of all slated determinants, I just call a summarize the set or describe it by D0. Here's some manifold, very beautiful manifold. These are actually exactly the manifold which underlies the Hartley-Fock ansatz in quantum chemistry. And now, inspired by quantum information, let's just imagine that the experimentalists prepare slated determinant states as classical mixtures. So we could just call it for fun, in quotation marks here, particle separable states, in the same way as we call now, in quotation marks, the slated determinant as the particle uncorrelated states. Okay? And then, inspired by quantum information, we could just introduce on a formal level measures of total particle correlation, C of rho, and entanglement, E of rho. Okay. And now you may wonder, can we calculate this? And on the level of entanglement, we are anyway always doomed for mixed states, but on the level of correlation, I have some very good news for you, because for the total particle correlation, one can actually arrive the closed formula. So it turns out that the distance of the quantum state rho to this black set can be calculated analytically for every state rho. So it's given by the particle hole symmetry for Neumann entropy S of the one particle reduced density matrix minus the entropy of the total state rho. Okay, so this means if you calculate this for pure states, for instance, for the ground state of your system, it's actually nothing else than a function, a very simple function of the one particle reduced density matrix. So you see here, from a completely different perspective, and motivate again the particle picture, emphasized again the relevance of the one particle reduced density matrix as a key object. And then last but not least, I mentioned entanglement. Calculating the entanglement is very difficult, but for a system of only 2 fermions and 4 spin orbits, one could get a closed formula. This was exactly a very nice contribution by Schliemann and Sirac and many other colleagues, maybe 22 years ago. Okay, so yeah.
What does it mean to subtract a density matrix from 1? Does it mean
so what I didn't mention here is it is different when you talk about fermions. The total state is always normalized to 1, but when you calculate a reduced state, like a one particle density matrix, we trade normalize not to 1, but to the particle number, which means rho 1 has eigenvalues because of Pauli between 0 and 1, and it's trace normalized to n. And then this one here is technically speaking 1. This means actually identity operator, not 1. The identity operator minus rho 1 is actually not the one particle density matrix, but the one whole density matrix. And so it's like a mathematical well-defined object just describing like the wholes rather than particles. So it's an identity operator minus rho 1. And it has also eigenvalues between 0 and 1, but then it's then normalized not to n, but to d minus n, where d is the dimension of one particle Hilbert space. Because then you have d minus n holes if you have d spin orbits and n fermions.
So sorry, but you start operating with this uncorrelated, unentangled, and separable states. I think you define uncorrelated, but unentangled and separable states were defined using this picture. And I'm wondering, on a more formal level, how do you distinguish between the uncorrelated, unentangled, and separable?
Actually, the picture can only place later as a summary of the definition. So definition was really like a state is called unentangled or separable if and only if you can express it as a convex combination of product states.
Okay, so you synonymously use unentangled and separable?
Yes, these are the same words already, unentangled and separable.
Okay, but why the picture was showing the different I guess there was if you go forward, correlation measurement and entangled measurement. So it seems like the blue triangle was for unentangled.
Exactly, or separable.
Or separable.
I mean, it's like synonyms.
Okay, but the two distances are unentangled. Okay, entanglement or correlation. Okay, so
correlation contains entanglement and classical correlation.
Okay, I see.
I mean, at the end, there's also something like there's also actually one correlation beyond entanglement, which I'm not discussing today. It's more complicated. But here, I just have like correlation, which should call also call it total correlation, and entanglement as a part of it. And you see, indeed, because the black set is a subset of the blue set, the total correlation is always larger, equal to the entanglement, which somehow reflects the fact that correlation could be classical or quantum in nature, could have both types, and entanglement is sometimes only the quantum part of the correlation.
Okay.
So now let's combine the quantum information and quantum chemistry, quantum many-body world to see, I mean, where this could lead us to. Since I'm motivated now, the one RDM as a very important quantity, let's actually talk about one of my favorite research fields, or methods, one particle reduced density matrix functional field. Of course, the main challenge there is to approximate the universal function. Okay, it's very difficult. But before you can actually think about functional approximation, you need to ask actually which domain does my function live in. And for fermions, you already know that not every one RDM is possible that you write down. There's some constraints in the Pauli principle. So it's illustrated here. There is a fermionic particle number operator for a spin orbital phi, and you know Pauli predicts that the occupation number is bound from above by the value 1. Now, if you restrict yourself to pure states psi, as I did here, it's actually more than Pauli. They're also so-called generalized Pauli constraints. They're very complicated. I don't want to introduce them today, but it's maybe good for you to know about them. For bosons, it's much simpler, even simpler at the end. If you have a system of n bosons, there's actually no non-trivial constraint. For n bosons, you can have both Einstein condensation, at least in principle. They can all occupy the same one particle states, at least from a mathematical point of view. But nevertheless, if you write down the space, or if you describe the space of all Hermitian operators for bosons, of course, it's not really constrained to say that the particle number cannot be larger than n. Because mathematically, we could also write down as alien if you land here and talk about one RDMs. Maybe you think you can have even negative eigenvalues or occupation numbers beyond n. Okay, so therefore, also this is a mathematically speaking a constraint. And the function that I was talking about, despite the fact that we don't know it, we know it's living exactly on this domain for fermions and on this domain for bosons. So now this is like about quantum chemistry, quantum many-body. So let's now add the quantum information facet to it. So in quantum information, there was exactly a mathematical breakthrough which revealed the existence of these guys. And this mathematical breakthrough even led to some further results, namely to a remarkable link between reduced density matrices whenever they are extremal in their allowed mathematical space, which actually means whenever you have a density matrix saturating some inequalities here and here, then the corresponding multipartite state, like it could be fermions, could be bosons, could be qubits, has a significantly simplified structure. So I can give you an example. For bosons, if I tell you they exist orbital phi such that this inequality is saturated, then you know how your state looks like. You just occupy the orbital phi with all n bosons and that's it. For fermions, it's very similar. If I tell you that there's a basis of orbitals for a fermionic system and the occupation numbers are all 1 and 0, then you know that your state takes the form of a single Slater determinant, right? So you see, extremality in the one particle density matrix implies global structure. And now, with this result connecting the 1 and n particle picture in mind, you can now go back to functional theory. Because in functional theory, it's about having a function which is about energy, and the function allows you to calculate effectively expectation values. So it's kind of a connection between energy versus n-terminal wave function indirectly, what underlies the functional theory. But now, since the n-particle wave function is connected to the one-particle picture, you have at the end a connection between the structure of the function and the properties of the one RDM. And then if you know a little bit about the mathematics behind these results and information, it's not that spectacular to formulate this conjecture here, namely that the gradient of the universal function with respect to the one-particle density matrix diverges repulsively on the boundary of the allowed domain. So you see the Pauli principle here for fermions, but then there are also generalized Pauli constraints which further reduce the size of this polytope. Okay. Now the statement is, whenever you send the one RDM close to the boundary and ask, how does my function change? You know that the gradient of the function diverges repulsively. This is universally true. We could prove it for all translationally invariant one-time lattice models, because there the advantage is you know the eigenstates to one are given. These are just momentum states which spin up and spin down. But there's no doubt that this result holds in general for each fermionic system, even without translation symmetry. We could just not prove it in a mathematical rigorous way. Okay? So it's really completely independent result of all properties of the system. You can have 2 fermions, you can have 10 to 23 fermions, you can have a neutron star, a 1D system, 3D system, a Coulomb interacting system, beyond nearest neighbor coupling, whatever you like. Any Hamiltonian, any property, you always have this force, this exchange force. It's exactly how we called it for fermions, divert exchange force. For bosons, we call this a Bose-Einstein force. And then you may wonder, okay, what is it good for? Well, some ideas. For fermions, for instance, from a conceptual point of view, it explains or proves that whenever you have interaction between fermions, you can never attain for occupation numbers the exact mathematical value 0 and 1. This is already known in mathematics or mathematical physics, but we provided a different explanation for this. And in the same fashion, we also provided a geometric explanation for quantum depletion. So if you're interacting bosons, you can never have perfect Bose-Einstein condensation. Yes, but here it's a purely geometric explanation. Then maybe if you know a little bit more about functional theory, maybe it's not surprising that these results here were found as part of a larger endeavor where we try to find at least the shape of the universal function. This is exactly what we managed. Since here, like for smaller systems, you see here a polytope as a cartoon. Here's the occupation number vector for translation variant systems. So these are just an occupation number vector of momentum states, momentum occupation numbers. And you see the exact function for small systems is nothing else than a sum of over every pair alpha and beta of facets. And then you essentially calculate for each occupation number vector the distance to their respective facets alpha and beta, distance d, take the square root and multiply it by the 2 electromatrix elements somehow. So you see for small systems at least, finding the function means nothing else than to understand the geometric system. And then for larger systems, you have to modify these terms a little bit by adding some parameters that no one can ever specify. And for bosons, it's essentially my student Julia Lieberter. She in her master thesis, she translated Bogoliubov theory into functional theory in order to get a universal functional valid in the regime of small quantum depletion. So now let's change to the overall picture. This is our second quantization. So remember, how do people actually exploit the structural simplifications in second quantization? So there's a scheme which is very, very popular since 30 years, namely DMARG. Okay, so this density matrix renormalization proof of ansatz has also now been applied in quantum chemistry since 20 years. And I was wondering, maybe 10 years ago, how do they do it? And where do the lattice sites come from? Then it was very instructive for me in my PhD to understand how this works. Well, you have an electronic Hamiltonian, you run Hartree-Fock for the system, then you get all the Hartree-Fock orbits, and then you just interpret these orbits as lattice sites. You know, it's like the 1s Hartree-Fock orbit, the 2s, 2px, and so on up to 17J, whatever. And then you express respect to this artificial lattice, your electronic Hamiltonian in second quantization, and you can call it lattice Hamiltonian. Okay, it will be not so local compared to the Hubbard model, but it's still like a Hamiltonian on a lattice. So now the hope is that when you now imagine the ground state of your system expressed in this basis here, that then the entanglement SL and SR between the left and the right side is much smaller than the one of generic quantum states. Because this would actually in turn allow you to truncate the still high dimensional Fock spaces of the left and the right half into much smaller dimensional subspaces, namely by taking into account only those dimensions of the reduced density matrix, row left and row right, that where they carry their main weight. Okay, this is exactly the idea of DMARG. But now, if you think about quantum chemistry, you may wonder, where does this local structure come from? And this is actually an ill-defined question, because if you choose the wrong orbits, there's no local structure. So the right question is, how should we choose in practice these reference orbits in order to get a maximally local structure? So this is like some ongoing research that many people care about, also we now since a few years. So let's say I pick a reference space phi k, make a very bad choice. And now I just illustrate to you here this pattern of correlation between orbit phi k and phi l. Now I wonder or ask you, please analyze this picture here, this pattern or this QR code or how you like to call it, and tell me how you would like, how we should update these orbits phi k to better orbits chi l or chi k in such a way that this entire pattern localizes much more. And as part of this endeavor or challenge, you also should ask, for instance, how local can it get? Because this is an ideal scenario, this is unrealistic. So you may wonder which part of the Hamiltonian determines how local this can get. You also may wonder, is it actually the orbital correlation that matters, or is it just the entanglement? Or should you go even beyond bipartite orbital entanglement? What's the right quantity? Another question would be, if we find the optimal approach to do this, I mean, when do you use it and how do you use it in practice? Because you don't want to calculate first the ground state and then analyze it, because then it's too late. So maybe the idea would be to use a cheap post-Hartree-Fock method, which can be run really quickly on the computer, analyze this pattern, and then based on this get better orbits, and then use your expensive method like Givenchy with high bond dimension or coupled cluster. It's like all ongoing. Many people work on this. Also, there's a nice paper, as I mentioned yesterday, to Arnold to you, but this Ursula Geertsen and Jens Eisert on orbital rotations. And recently, we also came up with the first ideas from my side in my group on method development and quantum chemistry. It's also about active space selection and quantum chemistry. So now let's change perspective to the quantum information side. Okay, asking you, can we talk about correlation or entanglement between orbitals? Okay. I mean, when we talk about particles, there was only bad news. So here, I have some good news for you. Orbitals, per definition, they're different because there's this lattice side here, there's this lattice side here, or this orbital and this orbital here. I mean, the definition is different. Therefore, we talk about correlation and entanglement in orbitals. And I tell you how this goes. Okay, it's not our idea, and it's very well known quantum information since more than 20 years. Okay. So you take your one part of hyperspace, let's say the one of your lattice, and you split this lattice into, let's say, left part and right part. You can do whatever you like. You can also split it in different ways. The occupied orbits in the Hartree-Fock picture and the unoccupied ones. Just split your one part of hyperspace. And now recall taking quantization and recall the occupation number basis. So now you can specify which of these lattice sites is occupied and which is unoccupied, and this gives you a basis, right? For the n-term in hyperspace or the Fock space. And now, at least on a very formal level, you just take this guy here and just cut it, for instance, in the middle and add a tensor product in between. And this is a very simple procedure, and this directly indicates to you that on the Fock space level, the Fock space of the entire lattice splits into a product of the Fock space of the left half and the right half. And this is what you can do also in the reciprocal lattice. Or you can rotate the one parted basis to any other reference space you like, and then you split the orbital basis in two or more subsystems, and then you're in a very good position because then you have a tensor product here, or in a couple of tensor products. Then you just apply what I told you about quantum information. You just identify these Fock spaces as subsystems. Okay. There's, however, one caveat that people in chemistry and quantum matter always overlook, that despite the fact that they're well understood quantum information, namely that this is so-called super selection rule. So nature does not allow one to coherently superpose a vacuum state in a one electron state. It doesn't exist in nature. Okay. And actually, by the way, if you just hypothetically imagine for a moment it was possible to violate the super selection rule, it would actually allow us to perform superluminal signaling. So we here in Toronto, we could send a signal to Europe instantaneously in time. This may not surprising because just imagine we can violate the selection rule. So you could imagine Alice here in Toronto could measure an observable given by a fermionic creation operator for an orbital here, plus the Hermitian conjugate, the creation and annihilation operator is a Hermitian operator. Now imagine Bob in Europe can do the same for an orbital in his system. So these two observables, these two Hermitian operators don't commute because you have just one creation operator here and one on both sides. They don't commute because they both have like odd parity. And then it's clear if you think about measurements and why it's relevant that observables commute. You have two operators which are spatially separated. They don't commute. So this also means if Alice here decides to measure her observable, it automatically sends a signal to Bob because his observable, despite the fact it's spatially separated, doesn't commute. So you see, there's some subtlety about thermometer. And now the point is, when you ignore the super selection, and just calculate the von Neumann entropy of a reduced density matrix, just by tracing out particles, you calculate nonsense. It's not the entanglement what you calculate, because you assume that the algebra of observables is larger than it actually is. And therefore, there are more states which are called entanglement. And therefore, you drastically overestimate the entanglement whenever you ignore super selection rules. Okay, it's only one caveat, maybe you don't need to worry too much about it, but it's good for you maybe to have heard about it. And whenever you would like to calculate entanglement in such a way that the quantum information scientists care about your numbers, then you have to take it into account. If you, however, only want to quantify electronic structure and don't care about quantum information processing, then it's absolutely fine to ignore super select rules, because then it's more about the structure of the state. So now you may wonder, okay, how should we now apply this in practice? Okay, so well, this quantum information approach is very versatile, and you can apply it in many different ways, because you can decide by yourself how you're going to split your system in 2 or more subsystems. In a lattice system, you can pick 1 orbit and a second orbit, or you can split it in 50 orbits. Or in a molecular system, you pick 2 orbits, IHA, and ask how are they correlated to each other. Or you pick even entire blocks of orbits and ask how is this block correlated to another block. So it's all up to you, and it's about understanding what's relevant for your research, and then for your problem, for your task, and then based on this, you make your own decision of splitting the system. Okay, just apply the formulas. So here, I think, however, that in quantum chemistry, 2 simple splittings, which are at the same time also the most relevant ones. The simplest one you can imagine is you just pick 1 orbit and ask how is it entangled to all the other orbits. So in chemistry, this will be about understanding active space structure here. It's about understanding which orbit contributes to the physics of the system and which orbit is boring and doesn't contribute because it's either doubly occupied or unoccupied because it lies so high in space. Or when you then go one step further, you pick 2 lattice sites or 2 atomic orbits and you ask how are they correlated to each other. This is relevant for valence bond theory, that that's about the correlation between orbits, localized orbits. So now, to get it right, so you understand correctly what we are talking about here. So the idea is you solve for the ground state of a system, let's say the chromium dimer or Hubbard model in 2D, then you get a very complicated quantum state psi n. But this is not Alice Bob. The psi n is not Alice Bob, okay? What Alice Bob is the following. You pick now a reference basis of orbits like Hartree-Fock orbits, lattice sites, momentum states. Then you pick 2 of those orbits, I in shape, and calculate the 2 orbital reduced density matrix, and even for each single orbital, the single orbital density matrix. Now, before we talk about subsystems, we wonder, actually, how do these guys look like? Well, before you write down a formula, you should always ask yourself on which space does the density matrix live. This should answer the question how you calculate it. So here I tell you this is a single orbital density matrix. So what could be the right Hilbert space? Well, it's quite obvious. Like if you want an orbital, it must be about Fock space. And a single orbital Fock space has 4 states for electrons: a vacuum state, spin up electron state, spin down electron state, and 2 electron states. So therefore, in some sense, this is a 4 times 4 matrix acting on C4. Therefore, rho IJ, despite the fact 2 orbits is a very small number, 2 orbits, is actually a 16 times 16 matrix. Okay, has 255 real parameters if you ignore symmetries. Okay, in practice, because you have fixed particle number, this guy is block them, and the particle number basis has spin symmetries. Many numbers drop out, but still like a complicated object. Okay, and now what's crucial for you to understand is this here is Alice versus Bob, the quantum information setting. You're asking now, how is Alice system, this orbital, correlated to Bob's orbital C4? Okay, this is like the total level, and this is our single subsystem level. Maybe just one result in between, which I would like to share with you. I told you calculating entanglement is very difficult for mixed states. It's almost impossible. And actually, until 2 years ago, there didn't exist any closed formula for entanglement applicable to electron systems which are spinful. Okay, and then my student Lexen, in his master's thesis, and then in the years afterwards, we managed to get the first closed formula, because formally you have to calculate this minimal distance, and actually with a lot of effort, Lexen managed to get a closed formula. I don't tell you too much about these details here, but you see it's a very complete formula depending only on 2 parameters, T and S, and this T and S just depend on some specific entries of this huge 2-particle reduced these two orbital reduced density matrix through HL. And now this is quite remarkable because now we have a closed formula. So now we can talk about total correlation, dissect into determinant and cluster correlation, and can calculate everything analytically, provided you have an analytical formula for the two orbital reduced density matrix. And I think this is very exciting. So now let's study one concrete application to wrap this up. So what's the single covalent bond? Well, in molecular orbital theory, they say there's a single covalent bond if a bonding orbital is doubly occupied, maybe by an electron pair. So this is not about correlation, it's only about occupation numbers. So this is not the right perspective for us here. But then there's a second perspective of bonding order, namely valence bond theory. There we learned in our high school time that there's a bond if two atomic orbits are kind of connected or coupled to each other. And this should ring a bell, because here the hope is now that quantum information would allow us to make this precise. This is exactly now what we're going to do on a very primitive level. So let's just look at one system to get some idea. You see here the system with many carbon atoms, and it's like essentially a linear structure. It's like a very primitive system that doesn't contain proper correlation, and you have some s orbits and some p orbits which are relevant. And here we just restrict ourselves to the so-called pi framework. Only the p orbits contribute, okay, because they can be decoupled. So we're talking at the end, think about 10 electrons in an active space of 10 pi orbits, okay? 1 to 0 to 10.
Sorry,
Yeah.
but what do you want exactly to make precise? I don't understand.
Okay, good question. So I want to make precise, it's like, what is the bonding order of the system? Because somehow in molecular orbit theory, there are now schemes how to make it precise. So you should get your wave functions by n, you determine what are the bonding orbits, what are the anti-bonding orbits, then you calculate the occupation numbers for all these orbits and subtract the occupation numbers of the bonding orbits minus the occupation numbers of the anti-bonding divided by 2, and this is the bonding order, and then it's maybe 3.4, and that's your answer.
Okay.
In valence bond theory, such a quantitative perspective doesn't really exist, because it's just more like qualitative. It's just say, two localized orbits are kind of connected, and then say there must be kind of a bond there. But now, in these quantum information tools, the idea would be take a diatomic molecule, cut it in the middle, and you ask how much entanglement is there between left and right, divide it by 2 times ln4 or ln2, and then this is the bonding order. And this would be like quantum information would allow us to turn the idea of a bonding order in valence bonding theory from a qualitative concept into a quantitative one. This is now the hope, and this is actually what's going to happen, at least for simple diatomic systems.
Okay. But it's quite quantitative when you were describing with the bonding and anti-bonding.
Exactly.
Right. So.
But there the downside is this actually has been proposed 10 years ago, and it was like a super, I don't know, to break through, but a very important work in quantum chemistry that you take explicitly a very complicated wave function, the one you got on your computer, and then exactly calculate the bonding order in the fashion as we discussed now. But the point is, if you think about a complicated system, particularly when it takes into account relativistic effect and there's some symmetry breaking, I mean, it's completely absurd what these people are doing to characterize each orbital as either 100% bonding or 100% anti-bonding. I mean, these orbits have different flavors. I mean, someone is more bonding than another one, and they cannot take this into account. And with this quantum information perspective, actually, at the end, it turns out all these aspects about how bonding an orbit is or not is automatically incorporated. And it's like the hope now that in the valence bonding theory, we have this advantage, so we could talk about correlation. And then, once you can directly see the H2 molecule, if you occupy the 2 bonding orbits and the 2 anti-bonding orbits with 4 electrons, I mean, you have two electrons, I mean, too many electrons. So the theory predicts that there's no bond there, because you have bonding orbital doubly occupied, anti-bonding doubly occupied. If you look at the quantum state, it's a quantum state where, I mean, at first sight, you have like 4 orbits occupied in each orbital. I mean, like bonding orbital will spin up, bonding orbital will spin down, anti-bonding will spin up, anti-bonding will spin down. All 4 are caught entanglement in left and right. But because the slate determinant of 4 orbits, you can rotate these 4 orbits in the subspace, and you can directly rotate it to a quantum state where you directly see that the left and right side are unentangled. And this is remarkable because it's just like 2 electrons created on the left side, 2 electrons created on the right side, and it's later determined thereof. And this doesn't contain orbital entanglement. This is a beautiful aspect of quantum information that it directly takes into account how bonding and anti-bonding orbits, when you simultaneously occupy them, how they counteract each other, and this leads to 0 entanglement. In the same way as it leads to 0 bonding order. But this is what you exactly want to make precise. And in this system here, you see when you talk about the canonical Fock orbits, which are highly delocalized, you get very small entanglement entropies compared to the maximum value that you could have from a mathematical point of view. But it's not surprising because the correlation between Fock orbits doesn't tell you anything about bonding order. So then I told my student Lexen to localize these orbits in this scheme. They can use the softwares and these quantum chemistry softwares to localize orbits. So for instance, PPEC may say localization, and I thought this sounds pretty cool. It must be the right thing to do. And then Lexen presented to me these numbers here, and then I was really disappointed because I thought if you apply localization, you must hit the ceiling, But this didn't happen, and then I couldn't believe it. But then we looked at the orbits, and you see, yeah, they're getting very localized, but it's still two center-like orbits. So then Lexen wrote a code to fully localize them, to reinforce them, localization to almost single centers. It's more or less autonomalized atomic orbits. And then you see these numbers, maybe you don't see it, there's a gray, light gray, it's going up to here. So then we almost hit the ceiling, and then we finally managed to describe the bonding structures. Maybe it's getting even clearer on this slide here. You see now going from single orbital entanglement, where I asked how much is an orbital correlated to all the other 9 orbits. I go to a slightly more sophisticated perspective. I ask here, you give me 2 orbits, I in shape, and ask you, and then we ask how correlated or entangled are they? And here there are 3 bases: Fock basis, PPEC Marseille basis, and Lexen's localized basis. Okay, and so you don't need to look at all these numbers here. Here's the total correlation that we introduced today. I didn't introduce today what quantum correlation is. So forget about this one. This is the entanglement, which is only a part of the quantum correlation, and this is the classical correlation. And what's now important is, if you look at these 2 columns here, it's a total mess. You don't see any well-pronounced bond structure because you don't have single center orbits. But this changed when you go to here. Here, they're fully localized, and therefore you discover this well-pronounced bonding structure because all these 2 carbon atoms are correlated, and then next to are correlated and form a bond. And what's I think very nice here to observe is when you talk about classical correlation or quantum correlation, total correlation, you see this light yellow background. Okay, this is like some extra correlation in the background. But when you start entanglement, you get that perfect pattern. Okay, and what you see in particular here is the following monogamy effect in quantum information. So tell you have Alice, Bob, and Charlie, and I tell you the quantum state of Alice and Bob is maximally entangled. It cannot be entangled. Alice's state cannot be entangled to the state of Charlie. It's like monogamy. And in quantum chemistry, you know de facto exactly the same, and this is exactly where it comes together. Namely, if you have, let's say, 3 atoms A, B, C, and I tell you this atom B should form a single bond to the left side, a single bond to the right side, and let's imagine this atom B in the middle offers only 1 single atomic orbital to form this bonding structure. This can never happen because a single orbital here can form either a covalent bond left side or to the right side, or 2 half bonds to both sides, or a delocalized bond. And this is exactly the monogamy effect of entanglement. So the atom in the middle needs to provide actually 2 orbits to form bonds to both sides. Okay, this is exactly the same effect, but from a completely different perspective. So now you can summarize this. So whenever you apply a localization scheme to fully localize the orbits, the molecular orbits, and then in the second step quantify the entanglement between any 2 orbits, this allows you to quantify bonding structures. Okay, in the sense of a single covalent bond then refers to 2 times Ln2 orbital entanglement. And this could be, for instance, used to settle some never-ending debates in quantum chemistry about what is the bonding order of C2. I mean, there's some people writing a paper in Nature Chemistry, it's like quadruple bond, and then 2 years later, another guy writes another Nature Chemistry paper, no, it's triple bond, and they don't stop anymore, these guys. And here with this one, you just cut the system in the middle, more or less, and then you get 3.4, and then it's finished. Because there's nothing more to be said. It should not be an integer because you have a complicated quantum state. You cannot assume that the textbook school stuff is true, that it's like triple bond or quadruple bond. So just 3.4, and that's the end of the story. So last but not least, okay, no, I think 1 or 2 slides. So now we may want, okay, so besides quantifying bonding structures, what else can we do? So now it's a well, given the nature of these quantum information tools, you can now analyze quantum states in order to change the numerical approach. So this is ideas also by Markus Reyer, Christopher Stein, and also by us now, the last 1 or 2 years, to analyze a collation pattern based on some cheap calculation beyond Hartree-Fock, like the DMRG below bond dimension, analyze this pattern, and then apply orbital transformation to simplify the bonding structure. So you see here we kind of condense more collation into a smaller active space, and this will then simplify the next steps in the numerical precision. So the general idea is use quantum information tools to analyze some cheaper intermediate quantum states in order to reduce the complexity of the transfer problem. And then last but not least, here this is from my point of view a very exciting link in apart from the orbital picture. I mean, I kind of oversimplify it here to make it not too mathematical at the end. One needs to specify a little more. But in words, you can say the particle collation is the same as orbital minimized orbital collation in the following sense. So in the particle picture, which is space independent, you just measure at least on a focal level the distance of your quantum state to the manifold of Slater determinant. Okay, this is like the measure of electron collation. It's ad hoc. There doesn't exist a quantum information perspective underlying it, but it's a very important quantity, this distance to the manifold of Slater determinant. Because if it was zero, Hartree-Fock would be exact. And the more you deviate from the Slater determinant manifold, the more complicated it is in general to describe the quantum state. So now it turns out, okay, up to some subtleties which I ignore here, the following holds true. So in the first step, you calculate the total collation in any two orbitals. This is a chromium diamond with 28 orbits, 1 to 3 up to 28. In any two orbitals, we have the collation. Okay? Now we sum up this 28, choose too many links, and get one number, namely the total collation in your entire system relative to your basis B, would be like the Hartree-Fock basis. Of course, this number depends significantly on the reference orbits. Now you could change Hartree-Fock orbits to maybe natural orbits, or you could translate it or change the orbits to localized atomic orbits. Well, and then you now try out all bases and minimize over all these bases, and then it turns out the minimum over all bases will coincide with the particle collation. This is exactly the statement here. So the conclusion would be, if you use a numerical method that refers to a fixed reference space of orbits like DMRG in quantum chemistry, or variation quantum eigensolver, where it's exactly the same, you pick also reference spaces, then you apply some unitary, for instance, unitary coupled cluster operator to build up your quantum state. Whenever you fix reference spaces, there's some people who use a fixed reference spaces, make a very bad choice, and say, this is a very complicated problem here, I cannot solve it with DMRG. But the point is to then at the end say, well, yeah, you perceived some overall complexity after having chosen a reference space B. But at the end, this total complexity can be split into two parts. One is intrinsic complexity, because if your quantum state deviates a lot from the state determinant, you can do whatever you want with the orbitals. It will be difficult to find the ground state. But a part of the complexity could be also due to your own inability to find good reference spaces. And then it depends on how smart you are. Some people have like extra complexity due to the wrong basis, which is very large, and some people are smart and find the right reference spaces. But this result exactly explains that there's an intrinsic complexity, the hardness of your problem, plus some extrinsic correlation to the suboptimal reference spaces. So with this summarized, so we shed light on the ground set problem from the QIT and quantum many-body perspectives together. We discussed the particle picture, the orbital picture. In the particle picture, we learned about intrinsic measures of complexity. Then I present to you this research highlight of my group in the functional theory, the diverging exchange force, the Bose-Einstein force, which we proposed. It would be, of course, very nice to measure them in a system which we call atoms. The orbital picture, if this formula, we derived the first analytical formula for orbital entanglement applicable to electron systems. This allows us in turn to dissect correlation effects in the classical quantum. Then this is like ongoing. We are now using these quantum information tools to understand how we should rotate reference orbits, how to pick active spaces, how to pick the optimal reference slate determinant for coupled cluster, tailored coupled cluster method in quantum chemistry, with the ultimate goal of reducing the complexity of the ground state. And then last but not least, I presented to you this very new idea that there's this amazing link between the particle picture and orbital picture. And then actually, from my point of view, the hope would be that this concept of intrinsic and extrinsic correlation related to this link would allow us to replace or at least complement This very important idea in chemistry, material science. It's a very important idea, but really dubious. I mean, it's really not it's ill-defined. Maybe the idea of static and dynamic correlation. There's like two types of correlation in the quantum state that are very difficult to deal with simultaneously, and all the chemists they talk all the time about them. And depending on whether static or dynamic correlation dominates, they use either this method or another method. And then when you have both types of correlations, it's almost impossible to describe the system. And then last but not least, like this fresh perspective, maybe we could advance a little bit or improve the methods towards the ground state, okay? By treating electron correlation in a more concise way, and then that way finding a more suitable approach to the ground state problem. And this will be, of course, relevant chemistry, physics, and material science, so everywhere. Okay, with this, I would like to